Okay, so our last topic for this unit, which again the unit's been, talking about advanced techniques of integration. We're going to, why am I pulling this piece of paper out? We're going to be looking at something called improper integrals. Okay. Improper integrals. Okay. So, we'll read through this here briefly and we'll get to some problems and stuff like that. The definition of a definite integral, okay, integral from a to b of f of x dx, requires that the interval over ab there be finite. Okay. Also, the fundamental theorem of calculus requires that the function is continuous on AB in order to evaluate the antiderivative. Okay. Here, though, we're going to look at a procedure that allows us to evaluate integrals that don't satisfy some of these requirements. All right. Integrals that have either one or both of the limits of integration as infinity, or as being infinite, right? Or they have a finite number of discontinuities. Those are known as improper integrals, right? So all the integrals we've done up to this point have been proper integrals. They followed kind of this idea that the definition, or that the definite integral is, over a finite interval, or there's no discontinuities in the interval too. But we're going to look at how to evaluate integrals that have infinity as one of their limits of integration, or that we have discontinuity. Okay, show up. So here are some kind of like scenarios that we could run into, right? Okay, so improper integrals with infinite integration limits. So one option, right, is that we could have our lower limit be finite, but we could have an upper limit of infinity. Okay, so it would look something like this, right? The integral from a to infinity of f of x dx. And the way we kind of fix that to make a finite limit here is we just make up this variable b, right, which is normally what we use for our upper limit there. And we just say the limit as b approaches infinity. So we're going to add a limit in front of our integral there to allow us to evaluate this thing. Okay, it's like, yay, even more stuff to write as we simplify things and work on it. So number two, right, we could have, alternatively, we could have our lower limit of integration be negative infinity, and then our upper limit be a finite limit of b. Okay, and then again, we fix it in a very similar fashion. We use a there. The variables don't matter. You can use whatever letter you want. I wouldn't use x, though, of course, because we already are using that in the function. But a is a typical one for the lower limit. And then finally, number three, we could also go from negative infinity to infinity, right? So we can evaluate like an infinite limit there, both to the left and to the right. In this case, even more fun, we get to break up our single integral into two integrals, one from negative infinity to a finite number c, and then from a finite number c to infinity, right? So we just break it up over c there, and then follow these kind of ideas here. Okay, c can be a number of your choosing. All right, c is a number of your choosing. Where you decide to break it up is kind of your choice. From what I've seen so far, it doesn't look like there's too much strategy involved. I mean, you can just kind of pick whatever value you want. So normally like 0 is a good choice or something. So, but anyway, we'll move on and see that. Okay. So in the first two cases, the improper integral converges if the limit exists. Otherwise, the improper integral diverges. Okay. So in other words, if we can, evaluate these integrals and then evaluate the limit, and we end up with a number, right? We say that those integrals are converge, right? If the limit exists, right? If any of these go to infinity, though, then we say this diverges, okay? Which means the limit goes to infinity or negative infinity, okay? Likewise here, all right, if just one of these diverges, the whole thing diverges, right? Because if you have one thing that equals infinity and you add a finite number to it, it doesn't matter. The overall value there is still infinite, right? So that's the idea, okay? So we're kind of mixing in our limits with our integrals now. And why not, right? So let's take a look here at this very first problem. All right, example 1, we want to evaluate the following integral. So the integral from 1 to infinity of d of x over the square root of x to the 5th. All right? Excuse me. So when we go to evaluate this, right, we're going to have to rewrite this. I got an upper limit of infinity, so we're going to start off by rewriting this as the limit. And since it's the upper limit, I'm going to use the limit as b approaches infinity of the integral from 1 to b. Okay, and I'm also going to take the time to go ahead and just rewrite my integrand, the thing we're integrating, right? What would be a helpful way to rewrite this integrand as? X to the negative 5 over 2 dx. Exactly right. Okay, that makes it a very nice, power rule problem. Okay? So now this is all nicely set up for us to now integrate. Now, since we haven't evaluated the limit yet, for our next step, you need to continue to write the limit as b approaches infinity here. Okay? For our work, because we haven't evaluated the limit just yet. All right? We can integrate now, though. So the integral of x to negative 5 halves, we'll add 1 to our exponent, so we get x to the negative 3 halves, and then divide by our new power, which dividing by negative 3 halves is the same thing as multiplying by negative 2/3. So I'm just going to do that, if you're okay with that there. And then we'll evaluate this from 1 to b. Okay. Again, we haven't quite evaluated our limit yet, so next step, when we go and evaluate here, we have to still write the limit as b approaches infinity of this thing, and now we'll plug in our upper limit and lower limit. So negative 2 over 3b to the negative 3 over 2 minus negative 2 over 3, 1 to the negative 3 over 2. Okay. So far, nothing too different. We just have to write this extra limit thing in front, right? And so I'm going to rewrite just one more step here. Some of you may, if you can evaluate the limit from this point, that's okay. Feel free to, all right? But I'm going to rewrite it just for our notes purposes here. I'll go ahead and make this plus 2 over 3 times 1 to the 3 halves. Okay. Sometimes it can be helpful just to kind of see it if we rewrite it one more step there, I guess I'll say. Okay, so again, the negative exponent, I move that into the denominator with a 3. Okay, so b to the negative 3 halves, move to the denominator, make it b to 3 halves. 1 to the negative 3 halves, move to the denominator, 1 to the 3 halves. Okay, and also it's minus a negative 2/3, so I made it plus positive 2/3. Now, we can finally evaluate this limit as b approaches infinity. All right, the only place we have a b is this upper limit right here. What will this approach as b approaches infinity? 0, right? As the denominator gets very, very large, okay, we're going to shrink this thing down to nothing, so it goes to 0. And then we can evaluate this right-hand part too, the lower limit, right? 1 to the 3 halves is just 1 times 3 is 3, so it's plus 2/3. And so 2/3 is our answer, and we can also say it converges. Okay, because it does not diverge, right? The limit exists. The limit exists, so it converges. Yes?
Can you explain the converge versus diverge again?
Yeah, sure. Yeah, sure. So I mean, basically, if the limit exists, if you do all this work and you get down to the final point here where you're like, okay, I get a finite number here, a finite number here, I can combine those two finite numbers together, then we know the limit exists and it converges. If, Carrie, you end up with an infinity or negative infinity in your final answer, then you know it diverges. It goes off to infinity. Okay? So, yes? Okay. What I plug in? So, I mean, I kind of did, I guess we could call it a direct substitution, or I just kind of evaluated the limit. I mean, if you imagine taking infinity and plugging it in here, you're going to do infinity to 3 halves, so it's still going to be like an infinity, times 3 is still infinity, but then it's negative 2 over infinity. So the degree of the bottom, you can think of it this way, the degree of the bottom is bigger, the degree of the top overall thing goes to 0. And then there's no b here to plug into, so this we can kind of ignore. So just this goes to 0 because of the limit, and then that's going to approach, simplify to 2/3, and then boom, 2/3. Okay? All right, let's continue on here and take a look at letter A. All right, so another, improper integral here. We're going from 1 to infinity. So we will have to rewrite, again, the limit as b approaches infinity, of the integral from 1 to b of, and I'm going to rewrite this as 1 over 2x plus 1 dx. Now, to do this integral, what technique are we going to need to use? We need to use substitution, exactly right. Okay, now, if you feel comfortable with it, some of you guys might be able to just go ahead and integrate this thing. You can kind of do the U substitution in your head. That's up to you. Again, just because it's notes, I will write out the U substitution there. Okay, so for U is going to be 2x plus 1, or du will be 2 dx, 1/2 du equals dx then. Okay. So here's where, I don't know, it gets a little hairy here because I'm going to say, so I guess I'm going to rewrite my limit thing, sorry. Okay, so I'm going to rewrite this then as the integral of 1 over u du, but we technically shouldn't have our limits of integration written in there from 1 to b because we're now in terms of u. These were our x limits of integration, so technically we shouldn't have our 1 to b there. You could, adjust your limits of integration if you wanted to, right? So for example, you could plug, the 1 in here. 2 times 1 will be 2 plus 1 is 3. So you could put 3 here, and then infinity would still be infinity. So you could probably just leave the b there, okay, if you wanted to. I'm going to leave it in, I'm going to do it this way instead. Just, I don't know, just because. But you could rewrite your, u limits of integration there and proceed that way. Anyway, we end up with, I forgot the 1/2 out front. Sorry, yeah, thank you. The 1/2 from the du substitution there. Okay. So, now we'll do that. So we get 1/2 natural log of the absolute value of u, right? And then we're going to evaluate that. Well, again, I don't want to put in the 1 and the b just yet, so maybe I'll hold off on that and just say that natural log, or limit of b approaching infinity of 1/2 natural log of u. Okay? But then we'll do our substitution here. 1/2 natural log of the absolute value, and we'll plug in that 2x plus 1. Okay, and now we can finally evaluate from 1 to b. Again, notice we're continuing to write that limit as b approaches infinity for all of our steps here because at no point have we evaluated the limit. So you have to keep writing that, okay? You have to keep writing that. And so now I'll plug in here. So we'll say the natural log of 2b plus 1 minus 1/2 the natural log of the absolute value. And I'll go ahead and just, so 2 times 1 is 2 plus 1 is 3. Okay. Okay. So here for our lower limit, right, it's finite because we just plugged in a 1 there. But for our upper limit, we have that b. Now we're going to imagine, plug it in, infinity here. 2 times infinity, infinity, plus 1, still infinity. Absolute value, still infinity. The natural log of infinity, well, natural log continues to increase, okay, without bounds. So this is going to be infinity times 1/2 is still infinity. So we're going to have infinity minus 1/2 the natural log of the absolute value of 3. Which means then, what can we say about this improper integral? Does it converge? It diverges, right? Okay, so this equals infinity, because really infinity minus 1/2 natural log of 3 is still just infinity. And so diverges. Okay. It diverges. All right? Question on any of that? All right. So let's take a look at letter B then. Letter B, we have both a lower and upper limit that's infinite. That's exciting. All right, so we're going to tackle that here. Remember that if we have both our upper limit and lower limit as being infinite, right, we have to split this integral up into 2 integrals. One from negative infinity to a chosen finite number c, and the other one from that chosen finite number c to then positive infinity. So let's just pick 0 here. Okay, let's just pick 0 because 0 is pretty easy to evaluate when it comes to things. So hopefully we choose wisely. Okay, so we'll take the limit as now a approaches negative infinity of a to 0 of 1 over 4 plus t squared dt. Okay, whoop, there we go. So there's our setup, but thankfully we don't have to do this is a pretty easy thing to integrate, right? What is the integral of 1 over 4 plus t squared going to be? It's going to be an arctangent, right? Okay, now we got to be a little bit careful here, right? Our u is t, our du thankfully is just dt, right? So we don't have to do any crazy u substitutions there. Our a is 2, Okay, 2, right? Because a squared is what we've got right there, 4, so a is 2. Excuse me. All right, so this equals, and now we'll have to continue writing those limits because we're not quite ready to evaluate the limits yet, but we can at least get the arctangents in there. So it'll be 1/2 arctangent t over 2, evaluated from a to 0, plus the limit as b approaches infinity of 1/2 arctangent t over 2 from 0 to b. Scoot out maybe 1. There you go. Okay. It's just a lot of writing. Okay. And now we can evaluate, right? Now we can just direct substitute our upper and lower limit in and solve. So let's see what we've got here. So we'll continue to write the limit as a approaches infinity, or sorry, negative infinity there. So we'll do 1/2 arctangent of 0, right? Okay. Minus 1/2 arctangent a over 2. Okay. So there's our first part with our substitutions, plus the limit as b approaches infinity. I'm going to try and squeeze this in here. I think I can do it. Arctangent of 0 minus 1/2 arctangent b over 2. Question? Yes.
Isn't it opposite when it be a 1/2 arctangent of b over 2 minus 1/2?
B first. You're right. Made a mistake there. Thank you. Upper limit minus lower limit there. There we go. Like, yes. B over 2, and then yes, 1/2 arctangent 0. Okay. So now we get to evaluate this. All right. So, arctangent of 0. Well, in other words, the question is tangent of what gives us 0? 0, right? And so it's 0 times 1/2, so we're just going to get a 0 there. Okay. So this is I'm just going to say equals 0. And then this other 1/2 arctangent of 0 over here, the minus 1/2, that's also just going to equal 0 right there. That equals 0, that equals 0. And then for our other piece here, we have arctangent of a over 2, which is really going to be negative infinity. All right? So we want to do negative infinity divided by 2, still negative infinity. We want to evaluate arctangent of negative infinity. Or in other words, we want to think about tangent of what gives us negative infinity. Okay? Well, believe it or not, this has a value. All right? If we go back to, if we remember, all right, what tangent looks like, the graph of tangent looks like, I'll kind of go over here and show you this here real quick. Remember, tangent, it's got asymptotes in it, right? Okay, at pi over 2 and negative pi over 2. Right? So, tangent of what gives us negative infinity? Negative pi over 2. So this is equal to negative 1/2 times negative pi over 2. Okay? Question, yes, Karen?
Does the arctangent do anything about it, or is it just simply use the graph of tangent?
So arctangent and tangent are related because they're exactly inverses of each other. So asking when we ask the question arctangent of negative infinity, that's the same thing as asking the question tangent of what gives us negative infinity. Because again, they flip with the x's and y's, stuff like that, because they're doing the inverse and stuff. So we're asking the same question essentially, right? But we're using tangent because I feel like tangent's just more familiar to us, you know, a little bit. Second part then, right? Now we're going to evaluate the limit as b approaches infinity, arctangent of right here, infinity, right? Infinity over 2 is still infinity. What is the arctangent of infinity going to be? Positive pi over 2, right? As we go to infinity here, right, as we go to positive infinity, we're going to approach that pi over 2 there. So yes, this is pi over 2. So it's equal to 1/2 times pi over 2. Okay, and so what do we have? We've got positive pi over 4 plus positive pi over 4, and so we have 2 pi over 4, which is then pi over 2 for our final answer there. Okay. It was 0, okay, minus positive pi over 4 there, but it was negative 1. I did the negative 1/2 times negative pi over 2, so it's going to be pi over 4. So 0, minus 1/2 pi over 2, but negative 1/2 times negative pi over 2 gives you that, and then 1/2 times pi over 2 there will give you the pi over 4 as well, and so you add them together, right? Because we add those two limits together there. Pi over 4 plus pi over 4. Okay. So this converges. This converges.
We're going to have to write that for this more time on this.
This is, let's see here. What does it say? I think, let me say this. I'm writing it now just to kind of like introduce the idea of it to us. I think just, I think with the directions, it says evaluate the improper integrals. So I think the pi over 2 would be sufficient there. But I'm writing that because later we're going to be talking more about diverging and converging and stuff like that.
So understand how as it approaches negative infinity, it'll be negative pi over 2.
Uh-huh.
But how did you know arctangent will go to pi over 2?
So for this second limit that we have to evaluate, we're approaching now positive infinity with b. So b, infinity, divided by 2, still infinity, arctangent of infinity. So then the idea is, if arctangent of infinity, that means tangent of what gives us infinity. So as we approach pi over 2, we're going to get the infinity there. Okay, that's the idea. Whew. All right, let's take a look here at this next one. All right. So here we want to evaluate the integral from 1 to infinity of 1 over p plus 4 minus 1 over p plus 6 there. Okay. And so we're going to use, again, we have to write our limits out, I guess I'll say, or whatnot, but let me see. Do I even have that? Okay. So again, we'll set it up here. We're going to take the limit as b approaches positive infinity of 1 to b, 1 over p plus 4 minus 1 over p plus 6 dp. And again, we can break this integral up over the subtraction there. So you can kind of imagine we're just going to integrate this, and then we'll subtract what the integral of this is, right? If you want to write it out, you can. I don't think it's not necessary to do this, but again, just to maybe help see it, I'll write it out. But you don't need to if you don't want to there. Okay, something like that. Excuse me. Okay. Do we need to do anything special here to integrate this stuff? The answer is right. Is no. We don't need to worry about that, right? So because we can just take the natural log, right? So if we wanted to, we could use a U substitution here. We'd say let U be p plus 4, but then du would just be dp, and so there's no need to like do any sort of corrections here. We can just go ahead and evaluate this. And so it's the limit as b approaches infinity of the natural log of the absolute value of p plus 4 minus the natural log of the absolute value of p plus 6. Okay, and again, we're going to evaluate that from 1 to b. Now, because we're subtracting these two natural logs, we could combine these two things together, right? When you have subtraction between two natural logs, we can make that what? Division. That's right, division. So let's go ahead and do that here. Make it a single natural log. Might help us out. P plus 4 over p plus 6. Excuse me. And we'll evaluate that again from 1 to b. And so then this is going to equal, we'll drop the limit now and say the natural log of b plus 4 over b plus 6 minus natural log of the absolute value of, and what's that going to be, 5/7. Oops, no, I still need to write the limit in there, my bad, because we haven't evaluated the limit yet. Okay. So we got that lower limit, no problem. It's just minus the natural log of 5/7. Or you can just, I don't need to have absolute values in there anymore because 5/7 is already positive. But what about b plus 4 over b plus 6? What will that approach as b approaches infinity? Well, the degree of the top is 1, right? The degree of the bottom is also 1 there. And so it's going to be like the ratio of the lead coefficients there, right? So it should just give us a 1, shouldn't it? I mean, that's what I'm thinking, right? It should just give us a 1 there. And so then we can just say it's going to be the natural log of 1 minus the natural log of 5/7. Okay? Again, degree of the top and degree of the bottom are the same. So the ratio of the lead coefficients there is going to be 1 over 1. Okay? If you want to, you could also imagine, kind of doing this with L'Hopital's rule. Excuse me. I'm going to kind of just pull that b plus 4 over b plus 6 out, but you get, if you see the, or you get infinity over infinity. If I apply L'Hopital's, though, it's going to be 1 over 1, and so we just get 1 there that way, too. Okay, we apply L'Hopital's there to that. So that is going to just get us 1. And so then, of course, though, what's the natural log of 1? 0. And so it's 0 minus the natural log of 5 halves. Or just negative natural log of 5 halves. 5/7. I can't read my own handwriting. That's pretty bad there. Okay. Thank you, Lander. Yep. Is that good enough? Or further up? Okay. Which, of course, negative natural log of 5/7 we could even further say is going to be the natural log of 7/5. Because that negative 1 in front could come in as an exponent, and 5/7, the negative 1, would become the natural log of 7/5. So, again, keep that in mind. Watch those natural log rules and stuff.
Did you write natural log of 7 minus natural log of 5?
If you wanted to. Mm-hmm. I guess I didn't bother doing that because, it could be that, though, yes. You could say natural log of 7 minus natural log of 5, yeah. I'll put that there, too. Why not? Okay. Questions on any of that? All right. So those are the kind of improper integrals where we are taking, we have infinite limits of integration. Now we're going to look at what happens when we are evaluating improper integrals with discontinuities. Okay. So if f is continuous on the interval from a to b, excuse me, and has a discontinuity at b, notice we are including a but not including b because we have a discontinuity at b. Then we can say the integral from a to b of f of x dx equals the limit as c approaches b from the left, right? We would be, in this interval, we would be approaching b from the left, and so we want to make sure we include that in our limit here, in our notation. So then integral from a to c f of x dx. So kind of a similar idea to what we were doing earlier, right? We're gonna use a limit to help us approach the thing that we otherwise wouldn't be able to evaluate. All right, same thing here with number 2. Now, if a is discontinuous, or if we're discontinuous at a, then we'll again use a limit, but now because a is the lower limit of integration, we have to approach a from the right in this interval. So we have c approaching a from the right there, and c is our lower limit of integration. And then finally for number 3, if f is continuous on the interval from a to b except at c, so that means there's a discontinuity for some c between a and b there, then we break up the integral at that discontinuity. Okay, so the integral from a to b of f of x, we just go from a to c and then c to b of f of x dx. Okay, so we're just breaking it up at that discontinuity. Okay, so, and I'm pretty sure pretty sure we're supposed to put, yes, you do have limits. There are supposed to be limits in front of these things here, I'm pretty sure, just like we have the limits here as well. So we will be using limits still with that, okay, to approach. We'll approach C from the left here. We'll approach C from the right here, okay? So anyway, let's take a look. All right, so evaluate the following improper integral. So now you'll notice here, the only thing that clues us in that this is an improper integral are the directions, right? And we can't always expect the directions to clue us in about the kind of integral we're going to have here. But what makes A an improper integral? What's the issue here? So yeah, Sean? Exactly. 2, our upper limit of integration would make our integrand it'd be undefined, right? If we have 1 over 0, and so that's the issue there, right? We're going to have we have a discontinuity at that too. So we have to use a limit here. We'll say the limit as B approaches 2 from the left, okay? From 0 to B. And again, I'm going to rewrite this as n minus 2 to the negative 3 dn, like that. Okay. To integrate this, what strategy or technique do we need to use? A U substitution. But again, this is kind of like a very basic U substitution where we can kind of like get away with like not doing it. If we imagine here, we're going to let U be n minus 2, du will just be dn, and so we can just really integrate this thing, you know, kind of, you know, mental math, the U substitution if you like. So that's what I'm going to do. Okay, so we'll add 1 to our exponent here, so we're going to have n minus 2 to the negative 2, and then divide by that new power. So dividing by negative 2 is the same thing as multiplying by negative 1/2. And we'll evaluate that from 0 to b. Okay. And again, still writing that limit because we haven't evaluated the limit yet. All right, now we'll do our substitution. Negative 1/2 b minus 2 to the negative 2 minus negative 1/2 0 minus 2 to the negative 2. Okay, and again, I'm going to take the step here to rewrite some things. So we'll make it negative 1 over 2b minus 2 quantity squared. I'll make it plus then 1 over, and then 2 times, well, all right, negative 2 squared there like that. Okay, again, it was minus a negative 1/2, so I made just plus positive 1/2 there. All right, so again, at this point, right, this piece, we can get a number for that bottom lower limit of integration when we substitute it in, right? It's going to be negative 2 squared is 4 times 2 is 8, so we get 1/8 there. But then if we take the limit as b approaches 2 from the left here, what's going to happen as we approach 2 from the left here? What is this going to approach? Well, so let's imagine here approaching 2 from the left. So approaching 2 from the left means we're going to be like 1.9, 1.99, 1.999, right? We're going to take that value and we're going to subtract 2 from it, okay? And so it's going to be a very, you know, small number, right? 1.99 take away 2 is like, you know, negative 0.001. We're going to then square that, so it's going to get even smaller, multiply it by 2, okay? And they're going to take negative 1 and divide by that tiny number. And so taking negative 1, dividing by a very small number is going to result in what? This is going to go to negative infinity.
Wait, what do you...
Well, it's the b minus 2 is going to get squared, so that's going to be positive, times 2 is still positive, but then negative 1 divided by that very small number makes it negative infinity. Okay, and of course negative infinity plus 1/8, whoops, negative infinity plus 1/8 is going to be just negative infinity there. That should be equals, and so this diverges, right? This one does not converge. Good stuff. Okay, questions on any of that? All right, letter B, the next one here. Why is this an improper integral?
Because we can't plug in 0.
Right, we can't plug in 0, so we have to break up this integral over the 0 there, okay? And so this is the way we'll rewrite this here. So I'm going to say the limit as, we'll do the lower limit, make sure I do this right, yes. So we'll say as C approaches 0 from the left, -1 to C of x to the -1/3 dx. And then we'll do plus the limit as C approaches 0 from the right of C to 8. Again, x to the -1/3 dx. Okay, so again, the first limit, we're approaching that 0. We're approaching 0 from the left, right, from values lower than C, from -1 up to the C. And so we want to approach 0 from the left, that first one. But then for the second one, we're approaching 0 from the right, because we're approaching from values greater than C, from 8 on down to the C of 0 there. Okay, so that's the idea. Okay. Thankfully, this integrates easily for us, all right? So we still have to write the limit as C approaches 0 from the left to 0 from the right kind of thing here. And so we get x to the, let's see, add 1 there, so you get 2/3 and a 3/2 up front. And then okay, C to 8. So there's our integration, and now we can do our substitution. So we'll say 3/2 C to the 2/3 minus 3/2 -1 to the 2/3 plus 3/2 8 to the 2/3 minus 3/2 C to the 2/3. Okay. Now, something really nice happened when we integrated, right? We had a negative exponent. When we integrated, we resulted in a positive exponent. And so now, if we try and direct substitute in 0 here, we'll have 0 to the 2/3, which is what? 0. Times 3/2, 0. And so we get 0, okay? -1 to the 2/3 is going to be +1, so it's going to be minus 3/2 there. Plus 8 to the 2/3. Well, here we want to be a little bit careful, right? 8 to the 2/3, it's you cube root the 8, so it's 2. Squared will be 4. And so we get 3/2 times 4, or just 6. And then again, substitute in the 0 for C. 0 to the 2/3 is okay, right? Earlier it was a problem because we had 0 to the -1/3 there. That's why we had to break up the integral. But now that we have a positive exponent, 0 to the 2/3, no problem. 0 times 3/2 is still 0. And so we have 6 minus 3/2, which is 9/2 there. So it converges. Okay. Yes, question, Kara. Sorry, say again one more time. Right. There, you know, maybe scenarios, I guess I'll say, when it's going to differ, it's going to depend, but in this case, right, in this case, it doesn't. Like, you know, from the left and from the right can depend in situations where you have like a piecewise function, I guess I would say, right? If you're integrating a piecewise function, to determine like which part of the piecewise function you would like plug it into, kind of thing. Also for like situations where if you want to know specifically if you're going towards positive infinity or negative infinity kind of thing. But here in this case, it just approaches that, you know, finite value there. So it's just 0. Yeah, we don't have to worry about that. So we go from something that was not continuous. We integrate it to be something then that is continuous, and so then we don't have to worry about, we can just plug in the 0 straight away kind of thing. Okay. So, all right. Making our way here. Just two more to do now. All right. These are the worst. No, I know these are pretty intense. It's a lot of writing too, and a lot of, you know, minutia you have to keep track of. Still writing all the limits and things and stuff. Minutia. Yeah.
Just this problem is the worst.
Yeah. Just this problem is the
Yeah,
worst.
just this problem.
Fine details.
Yeah, just this one.
Just this one. Okay. Well, let's take a look at it here. Okay. So
Dude, why?
we have an improper integral again, right? We're going to approach b. Sorry, we're going to let the limit as b approaches infinity from 0 to b of x e to the negative x over 3 dx. Okay. Or negative 1/3 x if you like. Okay. Why don't you like this one, Mario?
Integration by parts.
It is integration by parts, yeah.
Oh my god.
Yeah. I know.
Mike, you didn't see that?
Mike was like, how could these problems get any better? And then they did, right? It's like, it just keeps getting better, you know?
I'm clocking out for the day.
Clocking out. Because you want to go home and do this on your own, you know? You want me to spoil it for you?
No.
Right.
Okay.
Yeah.
All right, well, I mean, if oh, off the screen, sorry, thank you. I'll scoot it over, there we go. So I'm going to start over here just because I feel like I'm going to need some room for this, you know, maybe. We'll see. So let's see here. Let's pick our thing. So if Mario thinks we're going to be using integration by parts here, then we should let u be what?
X.
Yeah, okay, so again, I latte or I late, right? The algebraic comes before exponential. So we're going to say let u be x. That means the dv then has to be e to the negative x over 3. And so that means du is going to be just dx. And then, oh boy, to integrate e to the negative x over 3, I mean, technically that's a... I'm off the screen, sorry. Goodness gracious. Let me go up to here and then we'll go back to that integration by parts part. I'm just going to be all over the place here. To integrate e to the negative x over 3, we have to use what? A U substitution. Oh my gosh. It's like Christmas morning. We're going to use all of the stuff that we know, right? So I'm going to use a W substitution. Let W equal negative x over 3. So dW equals negative 1/3 dx. Or in other words, negative 3 dW equals dx. Okay. And so we'll get then that v is negative 3 e to the negative x over 3. Okay, when you do all that. Good times. All right, so for our integration by parts, then remember we do uv. So we're going to have negative 3x e to the negative x over 3. Zoom out just a skosh here. Can I get it all fit? Mostly. All right. So negative 3x e to the negative x over 3. There's our uv. And they're going to do minus, remember the integral, v du. So we're going to do minus the integral. Okay. And I'm going to pull that negative 3 out front here, make it positive 3. Integral of v, so e to the negative x over 3, du, thank God, is just dx. Okay.
Would you have to do your integration dilemma things?
Yes, limits of integration are from 0 to b there still. Okay. So we can continue our work here. We'll continue writing that negative 3x e to the negative x over 3 plus, and then integrating e to the negative x over 3, well, we just did that right here. You remember it resulted in negative 3 e to the negative x over 3, so we'll do 3 times negative 3 e to the negative x over 3. Okay, and then this whole thing will evaluate from 0 to b. All right, and then we'll continue writing our limit here. Limit as b approaches infinity. I'll go ahead and plug in my upper limit. So this whole thing, right, all the x's here, remember all the x's get a b plugged in, and then subtract, all the x's get a 0 plugged in too. Okay, so I'm going to make it negative 3b. I'm going to move this e that's to the negative x over 3. I'm going to move it to the denominator, make it e to then to the b over 3. And that's negative 9 over e to the b over 3. Minus. And now let's plug in 0, but I'm just going to do the 0 here. So it's negative 3 times 0, 0, e to the 0, so it's just going to be 0 there for that. And then let's see here. E to the 0 will be 1, so minus 9. Okay, so thankfully the lower limit is not that bad. Whew. And now we get to evaluate the limit as b approaches infinity here. All right. So let's imagine a direct substitution here. We're going to have b approaching infinity. So this is going to be negative infinity in the numerator. And then e to the infinity. So that's going to also be infinity here. And so this is going to be infinity over infinity. Okay. We end up with negative infinity over infinity, which means we can apply L'Hopital.
Man, sounds like it's
I don't know why this isn't Mr. Goff's favorite problem. I mean, I'm sure you guys are like putting up there in your top 10 right now, aren't you, somewhere? So to apply that limit then as b approaches infinity. Okay. Now, again, let me back up one step here real quick. We ran into this earlier today when we were talking about limits and stuff like that. All right. The numerator here is negative 3 times infinity. The denominator is e to the infinity. So even though we could say, yes, this is negative infinity over infinity, which one's going to get bigger faster? E to the infinity or just infinity? E to the infinity will, right? And so if our numerator is going to get bigger much faster than if our denominator is going to get bigger much faster than our numerator, what does that mean the value of this is going to approach? 0. And we can also say the same thing here, right? Only our denominator is going to be approaching infinity, so that's going to go to 0 too. So we can say it's going to be 0 plus 0, and the whole answer is going to be 9, okay? But if if you want to, you can also apply L'Hopital here. Just convince yourself. We do end up with negative 3, and then 1/3 e to the b over 3 like that. And if you plug in the infinity there, now you're going to get negative 3 over infinity, which is going to give us 0 there. Okay, so this is 0, this is 0, that's 0, and then that's going to be that's a negative 9, so minus negative 9 is going to be plus 9. And so this whole thing at the end is 9. Okay? There will not be 10 of these on your test on Thursday, all right? I don't even know if there's going to be one of those on your test on Thursday. That's that complicated, okay? Just because it's pretty crazy. Yeah. Right. Okay, so there's 9. There's our answer. Questions on number 5. We got one more here. We're almost done. That's pretty intense.
You sure you want to do this one?
So, yes, converges then. Exactly right. Converges, yes. Converges. All right, last one. We got this. We don't have time? No, we got time.
Nah, don't.
Just enough.
You sure?
I said you're doing good, buddy. I'm proud of you.
Just enough.
you. I'm doing the biggest work.
Good. A solid is formed by revolving around the x-axis, the unbounded region lying between the x-axis and the graph f of x equals 5 minus x from 1 less than or equal to x less than or equal to 4, and 4 over x for x values greater than 4. Find the volume of the solid formed given x is greater than or equal to 1. Neat. All right, so we're finding a solid, a solid's volume, I guess I'll say here, and we're going to, it's an unbounded region here, okay? So potentially like infinite, I guess. So we'll see how this is going to turn out, all right? But anyway, all right. To find the volume of a solid formed by rotating, right, we have to determine here, are we using discs or washers?
Probably washer.
So
Probably washer.
between the x-axis and the graph, and we're revolving around the x-axis. So actually, we only need to use a disk here.
Really?
Our boundary is the x-axis and the graph, and we're revolving about the x-axis, and so we don't need to worry about wash method. We're just going to use disks here. So we've got pi integral from a to b of our radius squared dx, right? That's our setup. Well, right, there is a catch, because what is our radius determined by here? Two different functions, and so that means we need to split up our integral over those two values here. Okay? Yes, there is a catch. So here's what we'll do, right? We are going to integrate. What's our first integral going to integrate from what to what? From 1 to 4, right? Because that is where we start with our first curve there, our first radius, and that'll be the curve 5 minus x, quantity squared, dx. Okay? Then we will add to that pi times the integral from 4 to infinity. That's right. Okay, square dx. That's right, all you Buzz Lightyears out there. To infinity. All right. But of course, this is not the proper way to set this up, right? We have to like... so we'll do the limit as b approaches infinity of pi times the integral from 4 to b of 4 over x quantity squared dx. Like so. Okay. And I think we'll stop there.
Yeah.
I think I'm just going to set it up. Okay? I think I'm just going to set it up. We'll stop right there. I know that it says to actually find the volume of the solid and stuff like that, but I think we'll stop right there. Okay? We'll take a break.
I appreciate it.
Okay? Because I think that's what I'm most concerned about right there. That. It's just setting it up. All right. So, that was a fun one, right? All right. Thank you guys for persevering through that. It was pretty great.
Basically,